Yes. This is the first question last year. We have a transfer function, and if we apply an input as 8-step function, what we get, and when t is equal to 0.24, what will we have? Okay. We have a transfer function which is gs is equal to 48.302 and 5 or by s square plus 10.842s plus 48.3025. An input UET is 8 UT. It means US will be 8 over S. Okay? How can we know it? From the Laplace transform table. Yes, here you can see the unit step function here. For the unit step function, the Laplace transform will be 1 over S. Okay. So, what we have for the ys will be, we know the transfer function is ys over us, right? So, the ys will be gs times us. It will be 8 over s times with 48.3025 over by s square plus 10.842s plus 48.302 and 5. How can we take the inverse Laplace of this function? Because we need it. The question is why, when, what is the time for the question? 0.2 and 4. We need 0.2 and 4. So we need to find yt before. Okay? How can we find? We will use Laplace transform table again. Can you see this? It can be the same with the maybe only for this part. For this part, can you see it is the same with second order prototype system, right? For the second order prototype system, we have already a transform where from the Laplace transform table. Yes, where is it? Here. You can see the Laplace transform table for the second order prototype system. But for this question, we have also an input 8 over s. So here we have also an s term. Okay? Because of this part, we have also s term. So what will we do? Maybe we have an inverse Laplace of it. Yes, you can see here we have and also s term here. So we can easily convert this expression to the time domain. Okay? Yes, 1 minus 1 over 1 minus xc square or the square root e to power of minus xc omega nt times with sine omega n square root of the 1 minus xc square times with t plus theta. What is theta? Theta is arc cosine of the Xi. Okay? So by using this expression, we can easily find the time response of this system. So, what is the natural frequency for this system? Yes, here. What do you think? What is the natural frequency? Yes, the square root of the 48.302 and 5. How can we know it? It is the same with the second order prototype system. So the omega n square is should be 48.302 and 5. Okay? So we can easily find 6.9 and 5. 6.9 and 5. What is the unit for the natural frequency? Radian per second. Okay? Radian over second. Yes. What about Xi? How can we find it? Xi should be 10.842 divided by 2 times 6.995. So it should be approximately 0.798. Okay, this is the damping ratio for this system. What we need for the inverse Laplace transform also. Yes, this is the inverse Laplace form. What we need also, theta. We need to find theta. It is arc cosine of the Xi. So, it should be what? 0.676 radian. Be careful here at this point. Of course, we should find it in radians. Why? If you do a unit analysis here, yes, here, if you do unit analysis, you can see it. This is radian over second, right? From the t, we'll get s second. So this part will be radians. So this part should also be in radians. Okay. So it should be 0.676. Now we can use the finding in solution. Yt should be equal to 8 minus 8 over by square root 1 minus xc square, sorry, not xc, 0.78 square times with e to power of minus 0.78 times with 6.95 t times with sine 6.95 square root of 1 minus 0.78 square times with t plus theta, which is 0.676. We need to find y 0.24. When you put t as 0.24, you will get the answer. Please do it yourself now. It should be approximately 4.56. What about the second question? The second question, put the t as 0.44 and find the solution for the first question. The right answer should be 7.38, 38 and 3, or 38 only. The other question is y 0.22, 22. Find the t is equal to 0.22 yt function. $4.13. Okay, what is the other question now? For the first question, find the real part of the roots of the characteristic equation. Find the real part of the roots of the characteristic equation. Yes, the result should be minus 5.42. How? Characteristic equation is s squared plus 10.842s plus 48.302 and 5 should be 0. When you do this operation, if you find the roots, you will get S1 and 2 minus 5.42 plus and minus J, yes, What is the imaginary part of the root? Results should be 4.35. 6 is about the damping ratio for the same question. We have already found it as 0.78. And 8 is about the natural frequency. We have already found it as 6.95. Okay. 6 is about the damping ratio. We have already found it 0.78, and for the 7 is about the natural frequency. We found it as 6.95. We can continue from 8. Here we have a function. Yes. We have a transfer function again. And only we should apply inverse Laplace transform and find the time response. That's all. This is the question. We can solve this question together. If we take this part, it is enough for us. Okay, the transfer function is gs is equal to 1 over s plus 0.04 to power of 2 times with s plus 0.63. That's all. We need to find g2. From the partial fraction expansion, we know it. gs can be written as a1 over by s plus 0.04 plus a2 over by s plus 0.04 to power of 2 plus k1 over by s plus 0.63. That's all. Now, how can we find the coefficients? K1 is s plus 0.63 times with gs, where s is equal to minus 0.63. So we get 1 over minus 0.63 plus 0.04 to power of 2. It should be approximately 2.873. A2 is equal to s plus 2.04 to power of 2 times with gs, where s is equal to minus 0.04. So it will be 1 over minus 0.04 plus 0.63, and finally we get 1.69 and 5. Okay, what about the A1? We have multiple order pole, so we should do derivative of s plus 0.04 to power of 2 times with gs, where s is equal to minus 0.04. And then we get 1 d over ds 1 over s plus 0.63, where s is minus 0.04. If we take the derivative, we get minus 1 over s plus 0.63 to power of 2, s is equal to minus 0.04, and finally we get approximately minus 2.873. Finally we get as g as a1, yes, a1 minus 2.873 over by s plus 0.04 and plus a2. What is a2 value? Yes, 1.695 over by s plus 0.04 to power of 2. And finally 2.873 s plus 0.6 and 3. So here we have a minus term, the first one. Now we can easily get the inverse Laplace of this function. How? Of course, by using the Laplace table, Laplace transform table. Let's look together. Yes, if the expression is as like that, we can convert it into the time domain as like that. Okay? By using it. Yes, by using it, minus 2.873 e to power of minus 0.04 t plus 1.695 e to power of minus 0.04, but here, as you see, we have a multiple order, so we need to look again. Here it is the same with our expression, so we can convert into the time domain as like that. We need also a t term here. Here we have also a t plus the last one, 2.873 e to power of minus 0.63 t. 2.873 e to power of minus 0.63 t. Okay. What is the question? Find the G2. If you put 2 value into this expression, we can get the answer as 1.29 approximately. Okay, this is the answer. What about the other question? 9. Get the sum of the coefficients of denominator. Yes, 9. Find the sum of the coefficients. You will get 1.6, 9, and 5. Here we have the coefficients here, here, and here. The sum of those coefficients will be 1.6, 9, and 5. What about 10? For this question, apply the initial value theorem and find the initial value. Limit t approaches to 0 gt. That's all. What is the result? Limit t approaches to 0 minus 2.873 e to power of minus 0.04 t plus 1.695 e to the power minus 0.04 t times with t plus 2.873 e to the power of minus 0.63 t. So from this part we get 0. From this part we get 1. From this part we get 1. Finally, it will be minus 2.873 plus 2.873. It will be 0. It is the initial value of this function. What about the other question? Question 11. Feedback may increase or decrease the stability of the system. Is it true or not? Yes, it is true. When the kisi between 0 and 1, the system will be unstable. False, yes, it should be stable. If the kisi approaches to 0, of course from the 1, okay? Assume that kisi starting from the 1 and approaches to 0, overshoot will increase. Is it right? Assume that kisi is 1. How can we get the time response as a graphical? Yt t, and assume that it is the reference value. It will be approximately as like that. Okay. If kisi is 0.7, how does it change? It will be approximately as like that. What if kisi is 0.2? What will be happen? It should be approximately as like that. So as you see here, when kisi approaches to 0, overshoot will increase. Okay? It is about this. The other question, generally closed loop system have more accurate control performance than open loop control system. So why we use the open loop system? It's about the cost of the system, okay? If you talk about the closed loop system, of course we have a measurement. It is mean we need to get a sensor and cost of the system will increase. So because of this reason, we can use the open loop control system if the control performance is not exactly important for us. Okay? Tau is time constant of the system. Is it true? Yes. Yes, this is the other question here. This is the circuit for this question. We have some values for the component. R is 0.6 ohm, as I remember. L is 5 millihenry and C is 8 farad. Doğru mu hatırlıyorum? Get the ILT as an output for this question, as you see, as an output, and find the ILS over ES. This is the question. And then find the value of IL 0.5. Then find the IL 0.5. Okay. Here we have a node, as you see, and here we have ILT. At this branch we have ICT, so we can easily write IT is equal to ICT plus ILT, right? And before the ICT can be written as CDECT over DT plus ILT. This is the first equation for us. And we can convert this equation into the Laplace domain. Assuming the initial values as 0, you can see the question. Initial value is assumed as 0, so we can directly convert this equation into the Laplace domain. How? IS will be equal to, this is not important, CS ECS plus ILS. Okay. What about the other equation? Can we write? Yes, here we can write a loop. As a loop, the sum of the voltages should be 0, right? So ET is equal to ERT plus ECT. We can write it RIT plus ECT, and if you use the first equation into this equation, we can get IT as RC DECT over DT plus RILT plus ECT. So we get the second equation. Of course, it is ET. And we can easily convert this equation into the Laplace domain again. How? It should be ES RC S ECS plus RILS plus ECS. Okay, please be careful what we want to find. We want to find this relation, right? So we can get an equation, and this equation should satisfy this ratio. Okay. If you examine this equation, the last equation, if we eliminate ECS, we can easily find the ILS over EC, right? Maybe we should examine the circuit again. What about ELT and ECT relation on this circuit? Yes, these are parallel branches, so we can use it, right? These are parallel branches, we can use it. ECT should be always equal to ELT because these are parallel components. Okay? And we can write LDLT over DT replaced by the ELT, right? This is the other equation. If you convert this equation into the Laplace domain, we can get ECS is equal to SL ELS. It gives the relation between the ILS with the ECS. Okay? If you put the last equation into the 3, last equation 5 into the 3, what we get? ES is equal to S square RLC ILS plus R ILS plus SL ELS. If you arrange this equation with respect to the ILS, S square RLS plus SL plus R, we get this. And finally, we can easily write the ILS over ES as 1 over S square RLS SL plus R. We can write the same equation as 1 over RLC over S square 1 over RC S plus 1 over LC. Is it right? What is the input for this question? If we apply as an input step function, what we get? Yes, if ET is equal to UT, ES should be 1 over S. Then we get ILS as 1 over S times with 1 over R times with 1 over LC S square plus 1 over RCS plus 1 over LC. Because we want to get a similarity between the second order prototype system. If you examine this part, you can see it. This is the same width. Because we want to get a similarity between the second order prototype system, now you can see this part with the similar width omega n square over by S square 2 kisi omega ns plus omega n square. Okay? Now we can easily find the omega n. Omega n is equal to square root of the 1 over LC. 1 over L is 5 times 10 to the power of minus 3 times 8. So it should be 5 radian per second. What about the kısi? Kısi is equal to 1 over RC over by 2 times omega n. So we get 1 over 2 times 0.6 times 8 times 5. Finally, we get approximately 0.02 and 1 as a damping ratio. Finally, we should find the theta value. It is arc cosine of the kısi. We get approximately 1.55 radian. Okay, now we can use the Laplace transform table. Yes, if you examine the Laplace transform table, you can see this is the similar with our system, and we can directly use the time response as like that. Let's do it. ELT is equal to 1 over 0.6 times with 1 minus 1 over 1 minus 0.021 square e to power o minus 0.021 times with 5 times sine 5 times 1 minus 0.021 square times t plus 1 plus 55 radian. This is the ILT. The question is, as you see, 0.5 ILT. You will get approximately 2.91. Yes, what about the other question? For this system, for the same system, get the state space model. How can we solve this question now? Please remember the last lecture, we can easily find if we have the transfer function of any system. We can easily find the state equation or state space model from the transfer function, right? So we will do it now. State space model is as like that. And we have already transfer function of the system, so A can be written as 0, 1. What about the last row? Minus A0 and minus A1. Remember that. What is A0? Yes, for this question. Yes, this is the transfer function for us. And we know this term is A0 for us. And here we should use minus A0 and minus A1. This term, this coefficient is A1. So we should write it into this matrix. 0 and 1. Ne buluruz arkadaşlar? We get minus 25 and we get minus 0.21. Okay, what about B? B, the coefficient of the input, it should be 0 and 1. What about C? C should be, as you remember, B0 B1, and it will continue as like that. But we have for this question only B0 and B1. B0 is this term 1 over R times L times C. It should be approximately 41.67 and 0. And D is already 0. The output function cannot include the inputs. That's all. Find the sum of the B1 and B2. And the last one, find the C1 plus C2. Yes, maybe you need to see here. Where is B1 and B2? In the state space model, it means B matrix. Add the component of the B matrix. It is the solution. Where is the C1 and C2? It is the output and sum of this component. That's all.